Okay. So, last class that we're talking about astronomy, and then on Tuesday we'll do final prep. I hope it's clear that if you've gotten enough of, 70% of the in-class assignments, 70% of the pre-class assignments, 70% of the homeworks, figure out how many of those are. You get full credit for that. That's 100 points. You know what you had in the midterm. That's technically a maximum of 100 points, and then there is 100 points in the final. If you want to do an extra credit, email it to me. All the slots are up. If you think of like, oh, this is a fun little thing, I'd like to talk about a constellation, or I have suddenly in the middle of the night a better mnemonic for OBA, fine girl, kiss me quick, or no, the quick is not in there. Quick, kiss me, that's where it ends. And it doesn't actually go to the L and T, so I think we have a better mnemonic on our hands. Great, send it to me. Extra credit is always welcome. So I can guarantee that I'll catch up on any late work if you hand it in before the end of Tuesday. After that gets tricky. My grader is already disappearing, sort of fading, because he's packing up his stuff and he's moving to California. So I think he might be out of here for the Derby, and so it's me doing the grading. So I do my best. After the 22nd, it'll be me grading, and it's best effort. So I usually get everything in, but all of you hand in 400 pieces of things to grade, I won't get it done. That's basically it. So I can guarantee I'll grade it if it's handed in for the 22nd. So, I was going to talk about cosmology, but I feel like I have to address this first, because we are talking about, strength of evidence. This is the kind of thing that science is all about, right? We have two ways of doing evidence. We can either go out and do an experiment, or observe what we see and convince our peers that this is the case. And let's just say my various news and social feeds have blown up with this particular news as of last night. Let's see, the Washington Post, Webb telescope detects a possible signature of life, so at least that says the word possible. Astronomers detect possible signature of life on distant planet is the New York Times. Bold claim, I would say. It all comes with this graphic in most cases. BBC scientists find strongest evidence yet, which is in quotes, which means that someone said it, of life on a distant planet. Then, of course, NPR, is this a hint of life of another world or just a lot of hot air? I think NPR is a little more skeptical on that one. And so, just to give you some Google around, this particular planet has been in the news before. This is a NASA press release. And so carbon dioxide in that K2-18b, that's the planet that we're talking about. And so what kind of planet is this? It is not quite a super Earth. Super Earth is just a little bit bigger. This is sort of like we don't have an equivalent in our own solar system. So this already gets hard, right? There's no good, it's a Venus on steroids or a Mars but slightly smaller. This is something, it's either a really, really big Earth, or it is something, but it's something the mass of Neptune. And so this is a new class of planets that we found from those transits, and it could be mostly covered by oceans. And so this was already a bit of a interesting topic. And there are many different kinds of, and this is just to give you an idea, this is out of one paper where they're trying to review all the different atmospheres that you could have on a planet like that, because it's also pretty close to its parent star, which is a brown dwarf, so not terribly warm. And so you can see, there's thermochemistry. Essentially, there's heat going into it, and you can have all these different chemicals in the atmosphere. And there's an ocean? Yes, there's an exchange between surface and atmosphere, or no, it's just a bare rock, or it is a molten rock. And so whether or not you even consider having an atmosphere that's a surface that's outgassing, put a bunch of volcanoes on it. So this was the first result. that we just saw the NASA press release on. And the blue line is the model, and the little white points is the data. And the data just squiggles all over the place, and there are a bunch of different molecules that sort of dampen or make these little troughs here. So you get methane, more methane, carbon dioxide, more methane, and then there's this dimethyl sulfide. So two methyls, what is that? That's a carbon plus a bunch of hydrogen on it, and then all of them stuck together to a sulfur molecule. More carbon dioxide and maybe more dimethyl sulfide. And so the result that came out today is this one, where they're really certain that they found that dimethyl sulfide in longer wavelength measurements. And again, this is the data, and that blue line is the model, and for that model you need dimethyl sulfide, which is not really convincing. It's not really convincing that that stuff is there, and it's really not convincing that that necessarily has to be life. It's something that, it's a sulfur compound that is often associated here on Earth with essentially microbial life. It's microbe farts or decaying microbes. So the claim was made by one team, and both interpretation and claim already met with quite a bit of skepticism, I would say, both online and in the press. Especially people going to point out that there's these very legible papers called Abiotic Reduction of Dimethyl Sulfide, Carbonyl Sulfide, and Other Organosulfur Gases via Photochemistry, Implications for Biosignatures and Metabolic Potential. That's not a title, that's an abstract. Not saying that we're good at pithy abstracts, because it's much easier to yell, oh my god, aliens. But this basically say like, hey, dimethyl sulfide I can make with photosynthesis alone. Like I can literally just bombard an atmosphere with photochemistry, and then you don't need to have life in there. And so this is sort of my final thing. This feels like way too much of a claim, and this is frustrating for anybody who goes, we've done this a bunch of times now. We've had a couple of times where it's just too attractive, or it's just too attractive for either the researcher or the, I don't know, the PR team of the university or the journalist, or everybody sort of wants to make that clickbait, I guess. And then you end up like, yeah, but this is not a bold claim, right? It doesn't go past our spidey sense. Our spidey sense is saying like, well, that's substantial claims, grand claims need grand data, and this isn't it. It is an interesting case, though, because it is a very high candidate for having a liquid ocean, and so there might be some really interesting chemistry going on here. You might not need bugs for that, though. So just to say, hey, this happens almost once a year. So every time I teach this class, it's either in the spring or the fall, I get to do this, where I go like, all right, well, we have this bold claim, and by the way, here's what the state of the field says, right? There's ways to do it without bugs. So, okay, I thought I'd give you that one, I try to put in the new stuff as much as I can. And there's usually an example of this, because it is tantalizing, right? But often you can get it from volcanoes alone. So we talked about Hubble's law. Like now I'm going to the cosmology part. But any comments on the life on other planets claim that you may have seen in the news or may not? Has anyone read that already, or was I the only one who was? Yep, there's a couple of people. Okay, fantastic. So, all right, I'm glad I addressed it. So Hubble's law, right? So we talked about a few things that Hubble's found that the galaxies were expanding, the universe as a result was expanding, everything was moving away from us. Does that mean we're in a special place? One, two, three. Thank you, by the way, for hanging on to your voting cards for the entire semester. Well done. We need them on Tuesday because we're going to vote through a whole bunch of questions, right? No, we're not in a special place because anywhere I go sit in this, bunch of galaxies, they all look like they are moving away from me. In fact, if whole universe is just expanding. And so there's that second part where that we know that there is that moment where light can start traveling through the universe, the cosmic microwave background radiation. This is one of those stories in science that we would have never made up as a writer, because they ended up through a combination of luck, perseverance, and other characteristics, we figured this part out. Because the implication was, well, if everything was smushed together, it had to be really hot. Where is the afterglow of that Big Bang? When do I see that, right? So that first moment, it's too hot for light to start traveling, but at some point it's big enough, it cools down enough that light can start going through the universe uninhibited. So that first light, where is it? And so this is called like that extremely dense and hot. Everything was ionized, meaning that the electrons were not separate from the atoms. And once it got recombined, that's when light can start traveling, right? So the universe was effectively opaque to light. So we have a couple of those times in the universe where it actually gets hard to see stuff because it hasn't been the universe is first ionized, recombines, and then later reionizes. And so these are the things that we're starting to look at. I just like this picture because if you want to look at like hearts to see, this is a great picture for that. At some point, however, the temperature comes down to 3,000 Kelvin. Electrons and protons form hydrogen, and then the photons can actually start moving through the universe. So now they can start traveling. It means that these are the oldest pieces of light throughout the universe. As it expanded, the light started as 3,000 Kelvin, but as it expands, their wavelengths get longer and longer and longer. And so the whole thing gets cooler and cooler, like a black body with a temperature of about 3 Kelvin, above absolute zero. So 3 Kelvin above absolute zero is so low that you expect very little in, you don't see optical light, you don't see a near-infrared light, you need to go towards the radio. Now, bit of history, bit of US history. There was a time where there was a company called Bell Labs. Who here has heard of Bell Labs at all? One person. All right. Bell Labs is odd because Bell Labs was a monopoly granted by the US government on anything with telephones. Basically anything with data. This was the company that sent your telegram. This is the company that you got your phone from. The idea was that way not 5 different companies are hanging telephone wires all over the city. I think it's in Manila. If you go there, there's like all these big trusses of lines going anywhere because this is basically every single company competing against every other company. And so the idea was like, you know what, we'll just grant you a monopoly, but you have to do it on the cheap. And so it has to be cheap for all customers. All right, fine. So Bell Labs, as one of the things they did, was have a very large research division, much larger than, say, even Google today, and comparatively to the size of the company. And so one of the things that was, like, they tried the first things they invented was the first tryouts for a communication satellite. So first they had a balloon, they bounced a radio signal off a balloon, and like, okay, this could work, and then they actually had the first communication satellite. And other things like, well, how can we make transistors, like basically how can we make the electronics that keep the phone system working better? And one of the things they built was this antenna in order to bounce a radio signal off that balloon. And 2 of their engineers were basically given the task, well, we still got this antenna, and we're hearing this weird hiss. Can you figure that out? So they were measuring the faint radio sources, and they had to remove all the effects that were happening, and they could just not get rid of the last bit of noise. And being good engineers, they were like, well, this has to be somewhere in our equipment, including, well, maybe it's the bird poop that's in the inside, right? So eventually they shooed away the pigeons, they tried to netting, they tried feeding them elsewhere, and I think at some point one of them just grabbed a shotgun and solved the problem, but it was very much let's go down everything that could possibly be resulting in this hiss? Because you can see this thing, you can direct it, right? You can point it at anywhere in the sky, and they were seeing the same hiss everywhere. And that low, steady, mysterious noise, it was still there. It was 100 times more intense than they had expected, evenly spread over the sky, suggesting it wasn't in our own Milky Way. Even the Milky Way is on one particular plane. So if we see it there as much as there as in the plane, that means it's coming from somewhere else. They got a Nobel Prize for this because that was the cosmic microwave background. That was the original noise, that's the original bang in the Big Bang. And this was predicted, but now they actually found it. And so they got this was the first Nobel Prize to go into this direction. This is sort of my Nobel Prize are an imperfect marker for whether or not interesting stuff is happening, because a lot of science is interesting, but this was a real neat breakthrough. And so, yes, this was found, and as a result, in 1989, NASA launched COBE, the very first of 3 satellites, to measure that, both the black body curve of the cosmic microwave background and how the cosmic microwave background changed over the sky. So, first, they made one of the most precise plots ever in science. This is a black body curve, and the red points is the data. It adheres exactly to a black body spectrum, like it is the most perfect black body. So if you look at any star or anything like that, there's usually some absorption. Here, it's a perfect black body, and the measurements are so precise that they just make crosses here because the error bar goes so small that you wouldn't see them otherwise. This is one of the best measurements we've ever taken, so yes, this is definitely a black body. And so that was a prediction by the Big Bang Theory, and that means that, yes, we have a Big Bang at the beginning of the universe, and look, there's the radiation emitted shortly afterwards. Oh, that was a note. That little note there was like, hey, there has to be a thing from like when 3,000 Kelvin, when you go from a black body of 3,000 Kelvin down to 3. And I feel like I've seen a movie of that, but I still haven't found it, so I owe you all that one. So if I want to look all over the sky, I can project it, so I can project it on the dome, which I will be doing at the end of class, or I can project it on something like this. This is called the Mollabite projection. You have other ones. You can see, if you own a globe or you've seen this, that everything is a little bit distorted. If you have to squish a globe and sort of unroll a globe and put it on a flat surface, flattish surface, then you're going to have distortions, right? So here Greenland is sort of almost over the horizon there. Antarctica looks enormous, but it isn't. It is, in fact, sort of the size of Australia, right? These things get distorted. So if I do the same thing with the black body radiation with COBE, first at the degree level, and this is a tenth, 100th, 1,000th of a degree, it's all the same. It's completely uniform. All right, let's subtract the black body radiation of 3.728 Kelvin and see if there's anything fluctuating at the thousandths of a Kelvin. Okay, this is what's happened at the thousandths of a Kelvin, right? So it's plus or minus 3.3, but hey, that blue blob here and that red blob here, we talked about it on Tuesday briefly. Why is there a blue direction and a red direction, right? We talked about there cannot be a special direction in the universe. That violates the isotropic principle. It has to be uniform in every direction. Why is that side blue and that side red? Anybody? Yes?
Because red direction is coming towards us,
Blue is coming towards us. Red's going away from us. Other than that, yes. Or is the universe coming in, is this part of the universe coming towards us and this part running away from us? Or what could be the alternative? Yes? We're going in this direction. This is our orbit around the center of the Milky Way. So we're seeing the motion of our solar system. So if you take that out, you go like, wait, that's just blue shift and red shift. That's our motion throughout the Milky Way. I can remove that, right? So, sorry, I had a multiple choice and forgot about it. So it is the Earth motion in the Milky Way. So basically B plus C is the motion of the Milky Way itself. So the Earth motion around the Sun, the Earth's motion in the Milky Way. You see this little dot here, that's that extra component. It is all our velocities combined that result in that. So that, if you take that out of it, you end up with this, and what could cause this little weird red band? Can anybody remember what that was? The planets, the Milky Way, dark matter, or the telescope? Which one was it? 21, 22. I don't have too many questions about cosmology, so, you know, I'm getting majority Milky Way. That's the plane of the Milky Way, right? So we still have a little bit of radiation coming off the Milky Way. Okay. Again, that is something we can fix for. And then what you are left with is these are the fluctuations so below 18 Kelvin, like micro Kelvin, a millionth of a Kelvin. We're now in little fluctuations of about a micro Kelvin, and then you see that there are cool spots and hot spots in the cosmic microwave background. So at the single degree, and this is sort of like at 3 Kelvin, you're, oh gosh, what is that in Fahrenheit? I should look that up and have that written on my hand. I'm so bad with Fahrenheit. It is well below zero, but it's 253 Celsius below zero, but that doesn't mean anything. Okay. Anybody wants to look that up, that's fine. My point was that at the one Kelvin degree, it is uniform, and the other two effects are below that. So once you get to a millionth of a degree, that's when you see small differences. And so, the universe was almost perfectly homogeneous, it was almost perfectly uniform, but there were very tiny differences in certain scales. Right? So this is this big blue blob, big red blob, and then smaller blue and red blobs. So the hotter areas, and then there are cooler areas. So these hotter areas have a little bit higher density than the blue areas. So remember that everything was so hot that even light couldn't travel through it. So it equalized as one system very, very fast. So something had to make stuff a little denser in some places and a little less dense in others. And so it's only 300,000 years old, so it's not a very big universe yet. And so what is causing these overdensities? And we think that's where dark matter already started to contract into some large places and already started to make voids. So the stuff was not spread uniformly. That was another Nobel Prize for the Kobe team. Right? So that was, hey, by the way, not only have we found the cosmic microwave background, but stuff is not, in fact, completely uniform. Okay, well, if NASA is told, this topic has now gotten 2 Nobel Prizes so far, would you like to try for 3? Obviously, yes. Yes, we would like that very much. Also, how big of a clumps are we talking about here, right? So, they launched the Wilkinson microwave anisotropy probe, right? This was to measure those little fluctuations in great detail. And then, of course, the European Space Agency also got in on the act and launched the Planck satellite. So there was a bit of an arms race to go. So we start with COBE. This is our map of little fluctuations. We go to WMAP and look, it's so much better at finding smaller scales. It's basically a bigger telescope. If you remember a little bit when I talked about telescopes a while ago, lambda over d, right? The wavelength that you observe at and the diameter of the telescope. If you know where you have the wavelength that you have to observe at, the only way to get more detail is to have a bigger telescope, to have more resolving power. Yes? Should I put the lights higher so that everybody stays awake better? I don't know. It's such a, I know, these are so comfortable seats. I have somebody take a nap here every class. It's fine, but I'll make it a little lighter. That way I can see everybody else a little better. All right, so WMAP did a much better job. But notice that the big blob here stayed a big blob of blue underdensity, but it is made up of smaller underdensities, right? So we start resolving that blob out. Same thing with the hot areas here. We're seeing still that hot area, but we're seeing what it's made of. And then with Planck, we get even slightly more detail. Again, it was a slightly bigger telescope, so we get even more detail than that. And so these are the three satellites that gave us the detail in the cosmic microwave background. So if you compare the resolution of COBE, you get really big blobs. If you get WMAP, you get more detail. With Planck, you start to resolve even smaller detail as you go in, right? So why is that interesting? So if I look at that, and I look at these combinations of structure, I go like, I've seen something like that before. And if I look at the large-scale structure of our universe, if I see how galaxies are distributed, they are in these fluffy, and some of them are really dense neighborhoods, and then you've got these big areas of nothing, and these trails, these lumps in between. So it's like, yeah, that looks like this is a void. It looks very similar, very reminiscent of that. So the early universe is not entirely smooth. And then as that's already an overdensity, so it's sort of as a, if you are 13 billion years ago and you already have a little bit of extra stuff, that means it attracts more things because it's got gravity going for it, right? So it becomes denser faster. And then if you're a little underdense, you're basically losing your stuff to these denser regions. So it starts a little bit out of whack, and then you have 13 billion years of growing more and more dense and more underdense. So those first lumps were important because we wouldn't, if it was perfectly smooth, then we would have a perfectly smooth universe now, and we wouldn't be here. This is one of those weird gates that you have to cross if like the universe wouldn't look like this, and sometimes the argument is we wouldn't be here to see it that way. If the universe hadn't been a little bit lumpy, it wouldn't have made galaxies, and therefore it wouldn't have lots of stars, several generations of stars. They wouldn't have made heavier elements. Planets wouldn't exist. Stars with galaxies wouldn't exist. We wouldn't be here. So that's called the anthropomorphic principle. Essentially, the argument is if I tweak the universe a little bit in this direction, we wouldn't be here to see it. So there's a strong one. It's like, that's what I just told you. Like basically, as soon as I dial this knob a little bit that way or this way, we're not here. Or there's a weak one. It's like, well, it would be very unlikely that we were here. The universe is pretty big. Like unlikely things will probably happen somewhere. So if you want to do a more detailed analysis, you kind of look like the size of the, so I'm going to go with this top here, the multipole moment doesn't mean anything, but how much of the image is in those blobs, so how big of those blobs mean what kind of size on the sky, right? So 90 degrees is, do I have blobs that are this big? And then if I get to half a degree, do I have blobs that are basically half my fist on the sky? And if I get to 0.2 of a degree, I'm getting closer to like my pinky. So how many of these blobs, how many of these different scales do I have, right? So I have a curious peak here at almost 1 degree. The universe seems to like 1 degree at this scale. And then not so much at half a degree, and then a little bit more again at slightly smaller, and then it keeps going like this. You see a whole bunch of points here. This is where we're doing the experiments now. Boomerang, for example, is a balloon-borne experiment. If building a whole satellite and then also asking NASA nicely for rockets to launch it into orbit is a little bit too much. You can actually go like, well, in the meantime, I can try my experiment on a really high altitude balloon. And so those are, high altitude balloons are used to do experiments as well, right? So if you have like, and so this is the part where I get the occasional audio file go like, oh, this looks familiar. Yes, this is the bass. And these are the vocals, and then the guitars are in there somewhere, right? This is frequency. So if I have really large, the blobs are over here, so this is the bass. And if I go to higher and higher frequencies, I see particular frequencies more often than I do others, right? So this is sort of the mixed panel for the universe. The universe likes certain tones and doesn't like other tones, right? It doesn't have many of those. Does this make sense on an intuitive level? 2 people nod, 3 people nod. Okay, good. So I think of like, yeah, I think of this as like the mix settings. I don't mess with this on my Spotify, but maybe you do. You go like, I can't hear the bass anymore. I'll dial it all the way up. And so that sort of is that ring down. So which tones the universe prefers, which sizes it prefers. That tells you what it's made of, right? So if it's a full universe, again, like if I blow on a bottle that is almost full, I get a high or a low tone. High tone, right? Because I only have a little bit. But if it's almost empty, I get a lower tone. Okay, great. Everybody's done this as a kid. That's still the same. Fantastic. Sesame Street and blowing on a cocoa. Same principle for like a church organ, for example. Long pipe, short pipe, long pipe's the bass. Sometimes in these church organs there are pipes in there, you go like, nobody can hear that. It's like, well, it does move their essential organs up and down, so people do sense that, right? So you have these different tones for the universe, and that tells you how full the universe is and with what. And about a quarter of it is full with stuff, and about 3/4 of it is filled with, as far as we can tell, energy. So that is a very strange mix. That's not what we were expecting. We were expecting way more stuff, and frankly, nobody was expecting energy at all. So if you started at the time of Einstein, or maybe a little bit later, so after World War II, what would you expect? I expect lots of hydrogen and helium throughout the universe. That's what the universe used to be made of. That dark matter wasn't discovered yet. And so really what we're ending up with is a tiny sliver of what we're known for, right? So this is sort of to illustrate that depending on how much you filled the glass, how much you filled the universe with, you can measure how much of the different kinds is in there. So what we're ending up with is 1%-ish of stuff that we can measure. Stars, everything else, and neutrinos. These are the things that we detected with telescopes. That's about 1%. And there's maybe 4% of gas flying around. Everything else is, we have no idea what it is, other than this is matter because it does gravity, it pulls it back in, and dark energy, which sort of seems to be blowing it out or pushing it outwards. So only 5% of the energy density of the universe is baryons, aka normal stuff. And so for me, this is almost we might want to rethink the whole term normal here, because if 5% of things is normal, then what is the 95 that the rest is made of? And so 73% dark energy, we have no idea what this is. It might be some property of vacuum of space itself. And so this is very interesting. We only just discovered this. And so just to give you an idea, if you fill a universe with almost uniformly with stuff, this is a redshift, basically how far back it is. So this is right at the beginning when we get the cosmic microwave background. So this is where it's almost homogeneous, but there's this little 1 in a millionth little fluctuations. But that's all I need, that's all dark matter needs, because then it starts pulling things together, right? So as we go closer and closer to redshift 0, which is now, you see stuff push together, and that's where that large-scale structure of the universe that I showed you, where galaxies live, right? So you get these walls, you get clusters, you get voids. That explains it, right? You have to have dark matter in order to make that large-scale structure. If I do this in gas and in stars, I'm going to do this with a slightly darker room. Sorry, people. So just dark matter seems to, that just does gravity, so as soon as you have a little bit of an overdensity, you end up with clumps of it together. Now, what forms in those clumps, initially we have one star go off, like that's the ones that we're trying to find, right, at really great distances. You see that gas is the first one to fall into those dark matter clumps. And then as we keep going in those denser regions of gas, that's where the first galaxies switch on. And as that keeps going, like, okay, here we've got a whole clump of gas, and there's where the first galaxies are forming. Here's another filament of gas, that's where some galaxies and stars are forming. So as that keeps going, that's where we're ending up with stars and galaxies. And not only that, the clumps themselves seem to concentrate as well, so you get groups and you get clusters of galaxies. So that explains the large-scale structure of the universe, and honestly, nothing else really does. You need dark matter, and then you need dark matter's gravity, most importantly, for everything to literally pull together. And so, yeah, now these days in our gamma survey, for example, you see these filaments and these big voids in between the galaxies themselves. We can only see these, right? We can only see the galaxies themselves. The gas is harder to do, but you could see it with a radio telescope, so that's the reason that we're building this enormous radio telescope in South Africa, and now also all the way up to Kenya, so there'll be a telescope the size of the continent of Africa, so this should be very interesting. And eventually you see everything sort of clumped together into groups, and larger galaxies form as, smaller galaxies clump together. So that works only if you have the gravity to begin with. Okay, fine. We don't know what the stuff is just yet. We'll figure that out eventually, right? So, but we've got its contents, we've got a rough content of the whole universe, and that's what we learned from the cosmic microwave background. Now, earlier we talked about Cepheids, and we talked about, hey, they're not bright enough to go very far. To measure distance, we can also do redshift with the new standard candle, the supernova, right? So this is the two different things that we do cosmology with. We see the expansion of the universe with standard candles, and we see how the universe formed right at the beginning. And these two things should match, right? Because as how the universe started and how the universe behaves today, that should match up. And so on Tuesday I showed you this, where, hey, there is a little bit extra distance for the redshift that I'm measuring the supernova at, and that was, yet again, the Cepheids could only get you this far. So we measure Cepheids to about here. We're trying to get Cepheids a little further so that, we calibrate on these points as well, making sure that everything fits right. This is 1998, and the two teams, red and blue, found a Hubble law that holds all the way to redshift 1, but most distant supernova look a little further away. This is a problem. The universe was accelerating. So that is what that dark energy probably is, but that acceleration of the universe, right now we see the universe expanding a little faster than it used to. And we expected deceleration. We expected the universe to be full enough that it was slowing down. If you have enough stuff in it, it would slow down, but it's not. That got them the 2011 Nobel Prize. So something fundamental is pushing out all the time. And that's called the cosmological constant, and this is called also something called vacuum energy. Effectively, it's a different label on something's pushing it out and you have no idea what it is. And so why do we call this lambda? Because originally Einstein stuck this in his equations to keep the universe static. He didn't like that it was expanding, or that his equation was for a general relativity, and the fact that we saw all the galaxies move out, that strongly suggested that you would end up with a universe that was expanding. He wanted to keep the universe static and eternal, and that he liked that a lot better. And so that was an example of fine-tuning. If you add something to your equation just to keep it to your liking, because you have an aesthetic problem with the fact that there's a big bang or there's the universe is expanding, why are you doing that? That's an aesthetic reason for you to do that. That is fine-tuning. So fiddling with your data or your theory until you like it better is a very human thing to do. And later he was like, nope, the data fits a expanding universe much better, and so he called it his greatest blunder. And so very unhappy Einstein, except that now it's back, except that it's pushing the other way. It's now pushing out in order to, instead of pushing in order to accelerate a universe faster than we think it should do. This is a big mystery, right? So both dark matter is a mystery, and dark energy, this pushing force, is a mystery. It's exciting because it means that we don't understand all physics yet. There's usually a moment where if everything fits together, you get these articles or thought pieces where people say like, well, now we understand all physics. There was, in fact, quite a bit of that in the beginning of the 20th century. Before quantum mechanics, before general relativity, there was a point where like, well, we're sort of filling in the last blanks, and then I think we know everything. Well, no. This is the wonderful part, right? There's a mystery out there to be understood. And that's what we're out for, right? So there are more Nobel Prizes to be got. I have personal issues with the Nobel Prize. You have to be alive to get it, and there's only 3 of you allowed to get it. So that is a bit strange because we've seen with for instance, the the gravitational waves got a Nobel Prize. But that was thousands of people that did the detection. And you would like the person who made the mirror, and like the person who figured out the laser, and you'd like the person who also did the measurements and the midnight shift to also get the Nobel Prize. This is a team effort. It is kind of like giving the Super Bowl exclusively to the quarterback. I don't think any sports fan would be a fan of that. Right? That is just weird. Okay, it's a 19th century artifact. The fact that you have to be alive is also one of those weird rules. Okay, fine. So as soon as you've got a bright idea, you've got to eat your apples. But it's the fact that it can go to a team is really an issue. And so we've got weird energy, weird stuff, and here's the part that we call normal stuff. These things: electrons, protons, stars, galaxies. What this is and what that is, we have no idea. So this might be a good thing to figure out, right? So a lot of the astronomical experiments now are either to figure out what dark matter is or figure out what dark energy is. Especially the Department of Energy, not NASA, not the NSF. The Department of Energy has a program called the Rubin Observatory in Chile, and it is to figure out more about dark energy. Effectively observe more of it so that we can actually understand what this vacuum property is like. When we got started with cosmology, so essentially the 1930s, we thought either you got a big bang and over time it's so dense that the universe would collapse back together. That's, if you're a fan of reincarnation, that is your universe, right? Because everything comes back into the big crunch, or the big gnap, and everything falls back together into a point and maybe restarts as a new big bang. Fantastic. Again, if you're a fan of reincarnation, the whole universe might reincarnate. But it's nowhere near that density, right? So we can have the perfect, so this is the density of the universe. If the density is exactly right, it will expand and slow down over time, but never quite stop expanding. The velocity that it's expanding keeps slowing down, never quite getting to 0. Right? There's a perfectly fine-tuned, and here's another fine-tuned option. So weirdly, I don't know, again, for mostly aesthetic reasons, most astronomers and astrophysicists hoped that it would be this one. And that hope sort of bled through as we're expecting omega 2. If it's a little less, it'll keep expanding, and it'll never really, at time infinity, slow down to 0, but it'll just always keep expanding. If it's 0, then it keeps expanding like this. It's essentially, there's nothing holding it back. There's no gravity pulling it back together. And this is where we're at. It's accelerating. It's actually speeding up. So empty is not empty is pushing out, which is very, very strange, right? So this is the reincarnation, as close to static as we can be. And what is this, right? So why are we expanding so much? Right, so is the fact that we live exactly at the time that we would start to differ, not a violation of the isotropic principle. We're at a special time in the universe where we can see the difference between the collapsing universe, the ever-expanding universe, and the accelerating universe. Yes, there's no place of time special. No, it's a principle, not a law. And I just want the semester to end. I'll put that in the last question. Voting is 1, 2, let's see this one be already, 3. Ophelia is always the same in April. All right, so I like it when artists actually take this information and do something with it. So we're here in our tiny solar system, and as we go out, we see that we're part of a Milky Way, which is part of a much, much larger structure of all these galaxies into this foamy structure all the way to the end where we see the cosmic microwave background. So that's sort of this is an artist's rendition of the observable universe. The further we look out from our little solar system, the older it all is. So eventually you hit, the age of the universe. Whatever's on that other side, we will never know because the light never got enough time to travel to us. So this becomes almost philosophical. It's like, are there galaxies here? Probably. How can you tell? We can't. Intrinsically, this is not the right question to ask. The universe is probably infinite, but there is a limit to how far we can see. All right. There's one more thing that we measure from cosmic microwave background, which is the current expansion rate of the universe. So we got that from how fast we saw the distances to supernova, we saw their redshift, so that got us a H0. That's the blue point. So it started in 2000 with the key project on the Hubble Space Telescope. So only after 7 years did the Hubble Space Telescope take enough measurements to get a measurement of the Hubble constant that was accurate enough. And so it was, between 64 and 80, sorry, this is 63 and 80, so basically 73 plus or minus quite a bit, but that was our measurement. Okay, happy with that. And then the first cosmic microwave background also gives us an expansion rate of the universe, the current one. And so this is the first one that came out of WMAP. And everybody was really happy. There's perfect agreement between the two measurements. We have a measurement at the beginning of the universe, we have a measurement that we're measuring how fast everything expands now, and they agree. Great, but that's not when we go home, because there's error bars. Let's see if we can bring them down some. Plus with our WMAP, this was the first year, third year, fifth year, seventh year. Yeah, it goes up a little bit, goes down a bit. Okay, that's fine. Meanwhile, the Hubble Space Telescope, this is the SHOES project. We have another project, like the SHOES project is another H0 measurement project. And it is also beating down those error bars. And they start to diverge a little bit. So I guess the measurement is still sort of here, but we have our uncertainty going this way and uncertainty going this way. And then about 10 years ago, they start completely diverging. In fact, the one that we get out of the cosmic microwave background from Planck and other measurements is much lower than the one that we get out of supernova measurements. This only has gotten worse. Again, exciting, because if there's a discrepancy like this at the 3 sigma, that means there's something we don't understand. Something is off between the beginning of the universe and as we measure it now. So we don't quite understand the expansion of the universe. Something's off. It's made out of dark matter, which we don't know what it is. And it also has some weird property called dark energy, which is blowing it out. So there's lots left to discover. I don't like ending up like we know everything, because we certainly don't. There's lots of mystery still happening to be discovered, and physics to be found. I have 2 more things. One of them is one of these, last one, about the cosmic microwave background, and then I'm going to switch over. That gives me time to switch over to the planetarium. Because Drew left me in charge, and I'm trying not to break it in the last week of the semester. So I'm going to go through with